I have a dream that one day
Let's look at what we mean by finite and infinite geometric series. Let's look at the series 1 plus 2 plus 4 plus etc. and in plus 128. This is a geometric series because our common ratio here is 2. In other words, we are multiplying by 2 each time to get to the next term. The important thing to note here is that we are adding a limited number of terms. In other words, we have a last term, 128. So this geometric series is a finite series. And the reason why it's a finite series is because we are adding a limited number of terms. In other words, we have a last term. Let's look at the same series. So 1 plus 2 plus 4 plus etc. In this case, we don't have a last term. We simply keep on adding terms. Since we don't have a last term, we have an infinite number of terms that we are adding. So this is known as an infinite geometric series, or an infinite series. Let's look at what we mean by a divergent and a convergent series. Now, an infinite series can be either divergent. In this case, we can also say that the series diverges, or it could be convergent. And here we also say that the series converges. Let's take an example. Let's take the series 1 plus 2 plus 4 plus 8, etc. Since we don't have a last term, it's an infinite series. Now, let's add the first two terms. So S2 will be 1 plus 2, which is 3. Then the sum of the first three terms will be 3 plus 4, which is 7. The sum of the first four terms will be 7 plus 8, which is 15, and so forth. And of course, we can keep on adding terms. Now, what we should note here is that as we keep on adding terms, the sum is getting bigger and bigger. So, as in the number of terms that we add approaches infinity, the sum to n terms becomes larger and larger. In other words, the sum to n terms also approaches infinity. In this case, we say that the sum to infinity equals infinity. Now, when the sum to infinity equals infinity, we say that the series is divergent, or that it diverges. Let's take a second example. Let's take the geometric series 1 plus a half plus a quarter plus an eighth plus a 16th, etc. Now, this is a geometric series because we are multiplying by a half each time to get to the next term. In other words, R, the common ratio, is a half. It's an infinite series because we don't have a last term. Let's take the sum of the first two terms. So that's 1 plus a half, which is 1,5. Then the sum of the first three terms. So that's going to be 1,5 plus a quarter. And that's 1,75. then the sum of the first 4 terms so we're going to add an 8th to 1,75. And that's 1,875. Then the sum of the first 5 terms, we're going to add a 16th to 1,875. So plus 1 over 16. And it's 1,9375. And of course, we can keep on adding terms. Now, what's important to note here, that as we add more and more terms, we are getting closer and closer to 2, the number 2. So as n approaches infinity, the sum to n terms approaches 2. So we can say that the sum to infinity is equal to 2. So we're going to get closer and closer to 2, never quite reaching it. The sum to infinity is equal to 2. In this case, the sum to infinity is not infinity, it's equal to a number. So we say that this infinite geometric series is convergent. Now it turns out that there's an easy way to tell when an infinite geometric series will converge. And this is known as the condition for convergence. So an infinite series will converge when R, the common ratio, is greater than -1 but less than +1. Otherwise, it will diverge. Let's take an example. Let's take the infinite series 1 plus a third plus a ninth and so forth. Now, in this case, R, the common ratio, is a third. If we take, for example, term 2 divided by term 1, we get a third. So the common ratio here is a third. Now, a third lies between -1 and +1. So we know that this series will converge. Let's take another example. So let's take 1 plus -1/2 plus 1/4 and so forth. In this case, the common ratio R, we can get it by taking term 2 divided by term 1. So R, the common ratio, is -1/2. Now, the number -1/2 also lies between negative and +1. So we know that this series will also converge. Let's take a last example. Let's take 8 plus 16 plus 32 and so forth. In this case, R, the common ratio, is term 2 divided by term 1, so 16 divided by 8, which is 2. The common ratio here of 2 doesn't lie between negative and +1. So in this case, this infinite series will diverge. In other words, the sum to infinity for this series will actually be infinity. So in example 9a here, we have to determine for which values of x each of the following geometric series will converge. And we are given these infinite series. So let's look at the first one. We have 2 plus 2x plus 2x squared and so forth. We start by finding R, the common ratio. And we can do so by taking term 2 divided by term 1. And we find that in this case, r is equal to x. Now, we know that for an infinite geometric series to converge, r must be greater than -1, but less than +1. So this simply means that x is greater than -1, but less than 1. Then in number 2, we have 1 minus x plus x squared, and so forth. Once again, we start by finding r, the common ratio. So taking term 2, which in this case is -x, divided by term 1. And r turns out to be -x. Note that in this infinite series, the signs alternate between negative and positive. So term 2 is -x. Because of course we can also write this as plus -x. So r is -x, and we know that for a series to converge, r must be between positive and -1. So that means that -x must be greater than -1, but less than +1. This, by the way, is known as a sandwiched inequality. So sandwiched. We want to isolate x here. So we want to get rid of this negative sign. And we can do so by multiplying through by -1. So -1 times -1 is +1. And recall that when we multiply or divide an inequality by a negative number, it switches around. So these two inequalities will switch around. -x multiplied by -1 is +x. And 1 times -1 is -1. Now, it's always conventional to write a smaller number on the left-hand side of a sandwiched inequality. So we merely flip this inequality. So -1 less than x less than +1. Then looking at number 3, we have x plus 1 plus x plus 1 all squared plus x plus 1 all cubed, and so forth. We can find r, the common ratio, by taking term 2 divided by term 1. So the x plus 1 in a denominator will cancel into the numerator. And we're left with x plus 1. So we know that x plus 1, the common ratio, must be greater than -1, but less than +1. We want to isolate the x here, so we can add -1 through. This is the same as subtracting -1 through. So -1 minus 1 is -2. Here, the +1 will cancel with the -1, and we're left with x. Then 1 minus 1 is 0. So for the series to converge, x must be between -2 and 0. Let's look at number 4. We have 3 minus 2x plus 3 minus 2x all squared plus 3 minus 2x all cubed, etc. So r here we can get by taking the second term divided by the first term. Once again, the denominator here will cancel into the numerator. And we're left with 3 minus 2x. So then 3 minus 2x will have to be between plus and minus 1. We can first get rid of the 3 here by adding -3 through. In other words, by subtracting 3. So minus 1 minus 3 is minus 4. Here 3 cancels with a negative 3. And we're left with negative 2x. Then 1 minus 3, of course, is negative 2. Now we want to get rid of the negative 2 here. Since we are multiplying x by negative 2, we can divide by negative 2. So negative 4 divided by negative 2 is positive 2. We're dividing by a negative number, so the inequalities will switch around. So negative 2x divided by negative 2 is just x, or positive x. And negative 2 divided by negative 2 is 1. Now, remember it's conventional to write a sandwiched inequality with a smaller number on the left-hand side. So we flip this inequality. So 1 less than x less than 2. So x must be greater than 1 but less than 2 for the series to converge. Let's look at the last infinite series here. We want to find the value of x for which this series converges. And we can start by finding r again, the common ratio, by taking term 2 divided by term 1. Now, this is the same as taking the numerator multiplied by the inverse of the denominator. Remember, the denominator is actually 2 over 1. We just don't write the 1. So the numerator multiplied by the inverse of the denominator, so by 1 over 2. And here we see that the 2's will cancel. So we're left with a third into x plus 1. Then we know for the series to converge, r must be between plus and minus 1. So that means that a third into x plus 1 must be between negative and positive 1. And we want to isolate x in the sandwiched inequality. We can first get rid of the third here, the fraction, by multiplying through by 3. So negative 1 times 3 is negative 3. Here the 3's will cancel. And we're left with x plus 1. 1 times 3, of course, is 3. Now we can get rid of the 1 here by adding negative 1 through. So negative 3 minus 1 is negative 4. The positive 1 here will cancel with a negative 1. And we're left with x. And then 3 minus 1 is 2. So x must lie between negative 4 and 2 for the series to converge. So let's look at your answers to this question. In each of these infinite series, infinite geometric series, we have to find the values of x for which the series will be convergent. So let's look at the first one. We start by finding r, the common ratio. So once again, term 2 divided by term 1. We can simplify this fraction by multiplying the numerator by the inverse of the denominator. So the numerator multiplied by 1 over 2. Of course, 2 here in the denominator is actually 2 over 1. So we multiply the top here by the inverse of 2 over 1, which is 1 over 2. The 2 goes into 4 twice, and now we're left with 2/3 x. We know that r must be between positive and negative 1 for the series to converge. So that means that 2/3 x must lie between negative and positive 1. We want to isolate x here in the sandwiched inequality, so we can multiply through by 3/2 to get rid of the 2/3 here. So multiply through by 3/2, then negative 1 times 3/2. Here the 2/3 will cancel with the 3/2, and we're left with x, and then 1 times 3/2 is 3/2. So this is our answer then. Let's look at the second series. Once again, we can find r by taking term 2 divided by term 1. And this, of course, is 3 minus x. So 3 minus x must be greater than negative 1. But less than 1. And we want to isolate x in the sandwiched inequality. We can first get rid of the 3 here by adding negative 3 through. So negative 1 minus 3 is negative 4. Here 3 cancels with a negative 3, and we're left with negative x. And 1 minus 3 is negative 2. We also want to get rid of the negative x coefficient here. And we can do so by multiplying through by negative 1. So negative 4 times negative 1 is positive 4. Since we are multiplying through by a negative number, in other words by negative 1, the inequalities will switch around. And negative x times negative 1 is positive x. Negative 2 times negative 1, of course, is positive 2. Now, as we mentioned before, it's conventional to write a smaller number on the left-hand side of a sandwich inequality. So we flip the inequality. So then 2 will be less than x, which will be less than 4. Moving on to number 3. We find r, so we can take term 2. So term 2 here, divided by term 1. So the denominator here cancels into the numerator, and we're left with 5x plus 1. Since r must be between positive and negative 1, we can say then that 5x plus 1 must lie between positive and negative 1. Then solving for x here, we can first get rid of the 1 here by adding negative 1 through. So negative 1 minus 1 is negative 2. Here the positive 1 will cancel with the negative 1, and we're left with 5x. Then 1 minus 1 is 0. Finally, we can divide through by 5 in order to get rid of the coefficient of the x here. So divide through by 5. So negative 2 over 5 will be less than x, which will be less than 0 divided by 5, which is 0. Then lastly, looking at number 4, r will be term 2 divided by term 1. And of course, once again, the denominator will cancel into the numerator, and we are left with 3 minus 2x.
So we know that 3 minus 2x must be greater than negative 1, but less than 1. We can first get rid of the 3 here by adding negative 3 through. So negative 1 minus 3 is negative 4. 3 minus 3 is 0, and we're left with negative 2x. This is less than 1 minus 3, which is negative 2. Now we can get rid of the negative 2 here as a coefficient of x by dividing through by negative 2. So negative 4 divided by negative 2 is positive 2. And once again, since we are dividing through by a negative number, the inequalities will switch around. Negative 2x divided by negative 2 is positive x. And negative 2 divided by negative 2, of course, is 1. We want the smaller number, the 1, to be on the left-hand side. So we flip this inequality. So 1 will be less than x, which will be less than 2.
For a convergent geometric series, we can find the sum to infinity by using this equation. S sub infinity equals a over 1 minus r. Here a is the first term, so the first term of the series. And r, of course, is the common ratio. So this equation only applies to a convergent geometric series. In other words, it only applies when r is between plus and minus 1. Let's take one or two examples. So let's take the series 1 plus 3 plus 9 plus and so forth. It's an infinite series because there's no last term. And the common ratio here, of course, is 3. Now, before we can apply this formula to work out the sum to infinity, we need to check whether this is convergent. In other words, whether this is a convergent series. So r in this case, we can get by taking term 2 divided by term 1, and that, of course, is 3. Now, 3 doesn't lie in this interval. It lies outside this interval. So this sequence, or this series rather, will be divergent. And immediately we'll be able to write down the sum to infinity. We know that for a divergent series, the sum to infinity is equal to infinity. Let's take a second example. Let's take 4 minus 2 plus 1, etc. Once again, it's an infinite geometric series, and in this case, the common ratio r, we can take term 2 divided by term 1, and this comes to negative a half. Now, negative a half does lie in this interval. So we know that this series will be convergent, and hence to find the sum to infinity, we can use this equation. So then the sum to infinity here will be a, which is 4, over 1 minus r, so 1 minus negative a half. So it's 4 over 1 plus a half, which is 1.5, or 3 over 2. And we can simplify this. It's equal to 4 times 2 over 3, which of course is 8 over 3.
Example 9b deals with very basic applications of the sum to infinity formula. In question 1 it says consider the sequence 16, 12, 9, etc. Determine the sum to infinity. So let's have a look at it. So we have the sequence 16, 12, 9, and so forth. And we must find the sum to infinity. We're first going to check that this is a convergent series when we sum the terms. So we work out the common ratio R, and we can take term 2 divided by term 1, and we see that R comes to 0.75. So from this we can see that R, the common ratio of 0.75, lies between plus and minus 1. And hence this is a convergent geometric series when we add the terms. So that enables us to use the sum formula for an infinite convergent series. The sum to infinity is A over 1 minus R. And we just plug in our values. A is the first term, and that's 16. R is the common ratio, and it's 0.75. And we can do this on a calculator, and we see that the sum to infinity is 64. In number 2 it says the sum of an infinite geometric series is 40, while the first term is 20. Find the common ratio. So we know that the sum to infinity is 40. We also know that the first term A is 20. Once again, we're going to use this formula. The sum to infinity is A over 1 minus R. And we can plug in our values. The sum to infinity is 40, and that's equal to A, which is 20, over 1 minus R. And we need to solve for R. 40 is 40 over 1, and we can cross multiply. So we have 40 times 1 minus R must equal 20 times 1, so 20. And we can divide the 40 into the right-hand side. So we have 1 minus R is 20 over 40, which is 0.5. And in solving for R, it's going to be 1 minus 0.5 or 0.5, which is 0.5. So the common ratio then for the infinite geometric series will be 0.5. In the third question it says, find the first term of a convergent geometric series with a common ratio of -5 over 6 and a sum to infinity of 6. So here we know that the common ratio R is -5 over 6. We also know that the sum to infinity is 6, and we must find the value of A, the first term. Once again, using this formula, we can substitute in our values. So the sum to infinity is 6. We need to find A, and R is -5 over 6. So it's going to be A over 1 plus 5 over 6. Now 1 plus 5 over 6 is the same as 1 and 5/6. 6 times 1 is 6 plus 5 is 11. So it's 11 over 6. On the left hand side we have 6, which is the same as 6 over 1. And we cross multiply. So A times 1 is A. And 6 times 11 over 6 is 11. So the first term then of this infinite geometric series will be 11. Let's look at your answers to this question. In the first one, we have this geometric sequence, and we must find the sum to infinity. So we have 6, 4, 2 and 2/3, etc. We're first going to check whether this is a convergent geometric series when we sum the terms. So we're going to find R, the common ratio, by taking term 2 divided by term 1, and we see that R comes to 2/3. In other words, R will be between plus and minus 1. So we know that we can use the formula for the sum to infinity of a convergent geometric series. We know that it's A over 1 minus R, and we can plug in our values. A is the first term, and that's 6. R we saw came to 2/3. And this we can work out on a calculator, and we see that it comes to 18. So the sum to infinity then is 18.
So let's look at the second question. It says the first term of a GP is 4, and the sum to infinity is 2 and 2/3. Find an expression for the nth term. So let's write down what we have. We know that the first term A is equal to 4, and the sum to infinity, so S infinity, is 2 and 2/3. And we can write this as 8 over 3. Now, we know that the sum to infinity formula is A over 1 minus R. So then A is 4. We don't have R. So 4 over 1 minus R must equal 8 over 3. Now we can cross multiply to find R. So 1 minus R times 8 equals 4 times 3, which is 12. Twelve minus 8, of course, is 4. And we can solve for R. It's going to be negative 4 over 8, which equals negative a half. Now, we need to find an expression for the nth term. And we know that we are dealing with a GP. So we know that T sub n is A times R to the n minus 1. We saw earlier that A is equal to 4 and R is negative a half. So negative a half to the n minus 1. So then we have an expression for the nth term.
So number 3, it says the sum of an infinite number of terms of the series 2 plus 2r plus 2r squared plus 2r cubed, etc. is given by 4 plus twice root 2. Determine the value of r correct to 2 decimal places. So let's have a look at this. What we have is the first term A. It's equal to 2. And we're told that the sum to infinity is 4 plus twice root 2. We need to find the value of R, the common ratio. So we're going to use the sum formula, or the sum to infinity formula rather. It's A over 1 minus R. We can substitute in. A is 2. Then the left-hand side we can write this over 1, and we can cross multiply. So we have 4 plus twice root 2 multiplied by 1 minus R. And this equals 1 times 2. Now we can divide 4 plus twice root 2 into the right-hand side. And we can solve for r easily. R will equal 1 minus the term on the right-hand side. So just making r the subject of the formula in this equation. And this we can find on a calculator. So it's 1 minus 2 divided by 4 plus twice root 2. And it comes to 0.71 corrected 2 decimal places. So r equals 0.71. Example 9c deals with simultaneous equations in a context of infinite geometric series. In the first question it says, the second term of a GP is 5 and the sum to infinity is 20. Determine the fourth term of the series. Our first step is going to be to write the information given as equations. It says the second term of a GP is 5. So we can write that t sub 2 equals 5. Now we can use the formula for the nth term. T sub n equals a r to the n minus 1. And rewrite this equation in terms of a and r. So t2 or t sub 2 will equal ar to the 2 minus 1. In other words, just ar. And this is equal to 5. And we have used this equation over here. We can call this equation 1. Then we are also told that the sum to infinity is 20. So we can write s sub infinity is 20. And now we can use this formula. The sum to infinity is a over 1 minus r. So we can rewrite this equation as well in terms of a and r. So then a over 1 minus r must equal 20. We can call this equation 2. Now we need to solve for a and r simultaneously. So we're going to divide equation 2 by equation 1. So it's going to be a. So a over 1 minus r, all divided by ar. And ar, I'm going to write as ar over 1 equals 20 divided by 5. So 20 divided by 5. We have a fraction divided by a fraction on the left-hand side. So we can multiply the top fraction by the inverse of the bottom fraction. Immediately the a's cancel, and on the right hand side of course we have 4, 20 divided by 5. On the left hand side now there's a 1 left over here. So 1 times 1 is 1. So just multiplying the numerators, and then 1 minus r times r, multiplying the denominators. So this equals 4. And the right hand side I'm going to write as 4 over 1. Now we can cross multiply. So r into 1 minus r times 4 equals 1 times 1. And we're going to multiply out the brackets here, or multiply into the brackets. And I'm also going to bring the 1 to the left-hand side. So it's equal to 0. I'm going to rewrite this quadratic. So it's negative 4r squared plus 4r minus 1 equals 0. Now we can divide through or multiply through by -1. And we can factorize this trinomial. It's actually a perfect square. So we take the square root of the first term, this sign, and the square root of the third term, and this is all squared, equal to 0. And in solving for r, 2r minus 1 is 0, so r is equal to 1/2. Now that we have the value of r, we can substitute it back into equation 1 in order to find a. So substitute r equal 1/2 into equation 1. Now recall that equation 1 was ar equals 5. So that means that a times 1/2 equals 5. And hence a will equal 5 divided by 1/2, which is the same as 5 multiplied by 2. So we see that a comes to 10. Now, to go back to the original question, it says determine the fourth term of the series. Now that we have a and r, we can use this equation to find the fourth term. So then t sub 4 equals a, which is 10, times r, which is 1/2, to the n minus 1. In other words, to the 4 minus 1, so cubed. And that's 10 times an eighth, which is 10 over 8. And this simplifies to 5 over 4. In the second question it says, the sum to infinity of a convergent geometric series is 32. The sum of the first 5 terms is 31. Determine the value of the common ratio. Once again, we're going to start by converting the information given into equations. So the sum to infinity is 32. So S sub infinity is 32. Now we can use this equation. S sub infinity is a over 1 minus r. And rewrite this equation in terms of a and r. So a over 1 minus r is equal to 32. And this we can call equation 1. Then it also says the sum of the first 5 terms is 31. So S sub 5 is 31. And here we can use a sum formula. S sub n is a into r to the n minus 1 all over r minus 1. And rewrite this equation in terms of a and r. So then, using this equation, we have a into r to the n, so r to the 5 minus 1 over r minus 1. This is equal to 31. And we can call this equation 2. We want to solve these two equations simultaneously. So once again, we can divide equation 2 by equation 1. So we have the left-hand side of equation 2. So that's to the r to the 5. Divided by the left-hand side of equation 1. And this is equal to 31 divided by 32. So on the left-hand side here, we have a fraction over a fraction. So we can multiply the top fraction. So the top fraction by the inverse of the bottom fraction. Now the a's cancel here, and r minus 1 into 1 minus r goes minus 1 times. So then on the left-hand side, we're left with negative 1 into r to the 5 minus 1. We can multiply the negative into the brackets. And we can make r to the 5 the subject of the formula. So r to the 5 will be 1 minus 31 over 32. Now, 1 is 32 over 32. So 32 over 32 minus 31 over 32 is 1 over 32. Of course, you could use a calculator here. And now we simply find the fifth root of 1 over 32. We could even use prime factors here. This is equal to a half. So the common ratio r then is a half. And this is in fact what we needed to find. Let's look at your answers to this question. In the first one it says, all the terms of a convergent GP are positive. The sum of the first two terms is 5. The sum of all the terms is 9. Determine the first three terms of the sequence. So let's have a look at it. It says the sum of the first two terms is 5. So we can write that T1 plus T2 equals 5. And now we can use the formula for the nth term. T sub n is AR to the n minus 1. And rewrite this equation in terms of A and R. So T1 is A and T2 is AR to the 2 minus 1. In other words, just AR. And this is equal to 5. I'm going to simplify this a little bit by taking out A as a common factor. And now we can call this equation 1. So equation 1. Then it also says the sum of all the terms is 9. Now, this is an infinite GP, or an infinite convergent GP. So we can use the formula for the sum to infinity. So the sum to infinity then will equal 9. And then using the formula for the sum to infinity is going to be A over 1 minus R that equals 9. And this we can call equation 2. We're going to divide equation 2 by equation 1. So we're going to have A over 1 minus R divided by the left-hand side of equation 1 is A into 1 plus R. So divided by A into 1 plus R. This must equal 9. So 9 divided by 5. So 9 over 5. We're going to simplify the left-hand side. We're going to take the top fraction and multiply it by the inverse of the bottom fraction. Now, just note that this is over 1. So we're going to multiply by 1 over A into 1 plus R. The A's cancel here. So then we're left with 1 over 1 minus R times 1 plus R. This will be a difference of squares. So it's going to be 1 minus r squared. We want to solve for r here, so we can cross multiply. 9 times 1 minus r squared is 9 minus 9r squared equals 1 times 5. So then 9r squared will be 9 minus 5, which is 4. And r squared will equal 4 over 9. So now we can get r by taking the square root on the right-hand side. But we are told that all the terms are positive. So when we take the square root on the right-hand side here, we can ignore the negative. So r will simply be positive the square root of 4 over 9, which is 2/3. Now that we have r, we can find a by plugging r back into, let's say, equation 1 here. So we can write, substitute r equal to 2/3 into equation 1. And equation 1 was a into 1 plus r is 5. So that means that a into 1 plus 2/3 equals 5. 1 plus 2/3 is 1 and 2/3, which is 5 over 3. And now we can solve for a. A will equal 5 divided by 5 over 3, which is the same as 5 multiplied by 3 over 5. So these cancel, and we find that a is equal to 3. So we have both the values of a and r. A is equal to 3, and r is 2/3. Now, we needed to write down the first 3 terms. So that will be easy now. So then our GP will be a, which is 3. R is 2/3, so we multiply 3 by 2/3 to get 2. Then we multiply 2 by 2/3 to get 4 over 3. So then these are the first 3 terms of this infinite geometric progression. So let's start by converting the information into equations. The sum of an infinite convergent geometric series is 24. So we can write that S sub infinity equals 24. And we can use a formula for the sum to infinity here. So A over 1 minus R will equal 24. And this we can call equation 1. Then it also says, if the same series is taken, but only the infinite number of evenly numbered terms, in other words t2 plus t4 plus t6, etc., are added, then the sum is 6. So from this we know that t2 plus t4 plus t6, etc., will equal 6. And here we can use the formula for t sub n and write these terms on the left-hand side of this equation in terms of a and r. So then term 2 will be just ar. Term 4 will be ar cubed. In other words, ar to the 4 minus 1. Term 6 will be ar to the 5, and so forth. This infinite sequence or series comes to 6. I'm going to simplify a little bit on the left-hand side. We can take out ar as a common factor. So it's going to be 1 plus r squared plus r to the 4, and so forth. So we're taking out ar as a common factor, and this is equal to 6. Let's look more closely at what is inside the brackets here. This in itself is an infinite series, with the first term a equal to 1 and the common ratio r equal to r squared. We are multiplying by r squared each time to get to the next term. So I'm going to use another sum formula here for the terms inside the brackets. So then this is a sum to infinity, and a is 1. So it's 1 a over 1 minus r, but we said r is actually r squared here. So this is the sum to infinity of the terms inside the brackets, and we are multiplying it by ar. So ar multiplied by 1 over 1 minus r squared will give us 6. We can simplify this. Ar times 1 is ar. And in the denominator we have a difference of squares, which we can write as 1 minus r times 1 plus r. We're going to call this equation 2. So now we have two equations in a and r. We have a over 1 minus r is 24, which is equation 1. And we also have this equation, which is equation 2. Now we can say equation 2 divided by equation 1. So it's going to be ar over 1 minus r times 1 plus r. So this is the left-hand side of the second equation. We're going to divide it by the left-hand side of the first equation, which is a fraction. So we can multiply by the inverse of this fraction. So we're going to multiply by 1 minus r over a. Now we can divide the left-hand sides of the two equations. So it's 6 divided by 24. So 6 over 24. The a's cancel here. 1 minus r cancels with the 1 minus r here. And we're left with r over 1 plus r on the left-hand side here. And this must equal 1 over 4. We can cross multiply. 1 plus r times 1 equals 4 times r. And in solving for r, 3r equals 1, and hence r will equal a third. Now that we have r, we can plug it back into equation 1. So into this equation to get a. So then a over 1 minus r equals, and we saw that this was 24. So it's equal to 24. So it's a over 2 thirds equals 24. And once again we can cross multiply. A times 1 is a, and that equals 24 times 2 thirds. And of course 24 times 2 thirds is 16. So we have the value of r, and now we also have the value of a. Now to go back to the question, we wanted to calculate the first 3 terms, and we can do this easily now. So then the GP will equal a, which is 16. That's the first term. And then to get to the second term, we multiply by r. And we saw that r was a third. So 16 times a third is 16 over 3. And then 16 over 3 times a third is 16 over 9, and so forth. Then coming to the last question here, it says the sum of the first and second terms of a convergent geometric series is 30. The sum of all the terms is 54. Determine the positive common ratio and the first term. So the sum of the first and second terms, so that's T1 plus T2, this is equal to 30. And we can write the left-hand side here in terms of A and R. Term 1 is A, and term 2 is AR. So this is 30. And we can take out A as a common factor. And this we can call equation 1. So equation 1. Then it also says the sum of all the terms is 54. So that means that the sum to infinity is 54. And in using the equation for the sum to infinity, A over 1 minus R. So A over 1 minus R is 54. And this we can call equation 2. Now we divide equation 2 by equation 1. So then dividing the left-hand sides, it's going to be A over 1 minus R divided by A into 1 plus R. So I'm going to multiply by the inverse. So 1 over A into 1 plus R. And this must equal 54 divided by 30. Now, the a's cancel on the left-hand side. So we're left with 1 over 1 minus R into 1 plus R. And we can simplify the right-hand side. This is going to be 9 over 5. We can also multiply out these factors in the denominator. It's a difference of squares, so it's 1 minus R squared. We can cross multiply. And in 9 R squared will equal 9 minus 5, which is 4. And R squared will equal 9, or rather 4 over 9. So 4 over 9. Now, we were told to find the positive common ratio and the first term. So when we take the square root on the right-hand side, we don't have to worry about the negative. So it's going to be the positive square root of 4 over 9. And this, of course, is 2/3. Now that we have R, we can substitute it back into equation 1. So substitute R equal to 2/3 into equation 1. So equation 1 says A into 1 plus R equals 30. So that means that A into 1 plus 2/3 will equal 30. This is 1 and 2/3, which is 5 over 3. And we can divide the 5 over 3 into 30. It's going to be the same as 30 times the inverse. And this is 18. So the first term is 18, and the positive constant ratio is 2/3.